now that we've talked about Lewis structures, I'd like to take around 10 to 15 minutes to talk about resonance. Resonance happens when we have the ability to delocalize a charge around the atoms of a molecule so that there's not such a charge polarization at one point and the molecule can become more stable. The first example that we're going to do is this formate anion, which is CHO2-. Note that when I say O2-, I mean O2, and then the charge is -1, just in case you're doing this more on audio than on video, but hopefully you're looking at the screen as well. You can start by drawing the skeletal structure. I'm just going to jump right into it since I don't want this video to be too long. You should have already watched the Lewis structures video, so this should be a fairly easy one to throw down a skeletal structure and understand what's going on here. So we're just going to draw our carbon, hydrogen, 2 oxygens. Now, you'll recall that carbon needs to make 4 bonds. And I can't really double bond this hydrogen because hydrogen, as you recall, the electron configuration is just 1s1. There's just 1 electron in that outer shell, 1 proton, 1 electron, and we're good. So we can't double bond hydrogen. What we can do is we can place a double bond to one of these oxygens. Now what this does is it means, recall from our Lewis structures video, that an oxygen with 2 bonds has 2 lone pairs, and an oxygen with 1 bond has 3 lone pairs and a negative formal charge. Now, this would work, all this stuff would be a-okay, except for the fact that there's really no selectivity as to which one of these oxygens is double bonded to the carbon. So this gives rise to our resonance structures. And I'm going to erase this so we can kind of start fresh on our skeletal structure. So, again, right, one of these oxygens can be double bonded. The O's will have a double bond. And this is a-okay, but again, as I said before, there's no selectivity as to which oxygen that is. So we can actually draw 2 structures, one with each as a double bond to a different oxygen, and then we can draw conclusions about how this molecule readily exists in its normal state. So we draw our first resonance structure. I'm just putting the H at the top. You don't have to put the H at the top. You can. I like to show my formal charge on the atom that's actually got that charge as well. So I know you're putting your brackets and doing your total charge. Anyway, I just like to include it to remind myself which atom has that charge that's giving rise to the total charge on the molecule. So these 2 resonance structures, and I'm going to redraw this second bracket here a little cleaner for you. These 2 resonance structures describe really well how this formate anion exists. And the reality is, it actually exists as a hybrid of both of these things. When you go to organic chemistry, you'll draw hybrid resonance structures on bond line drawings all the time. I'm just going to show you. You don't need to write this part down. You won't be asked, at least by me, to draw hybrid resonance structures in general chemistry. However, so for a hybrid resonance structure, you obviously just throw down the skeletal structure as normal. And then everything that appears in both structures, right? So in both structures, this oxygen has at least 2 lone pairs. Notice that in this one, it does not have that 3rd lone pair. In this one, it does. So I draw 2 lone pairs on this oxygen. The same is true for the other oxygen. And then, right, half the time there's a double bond to this oxygen, half the time there's a double bond to this oxygen. So I make this little dotted line to show that actually this anion as a whole, also these partial charges, partial negative charges go on each oxygen. Those little D-looking guys are lowercase Greek deltas, and they just symbolize partial charge, so that plus or minus will indicate whether it's partial positive or partial negative. Both oxygens turn out to have a partial negative charge, because in one resonance structure for each, they have a negative charge. That's better. So, again, you don't need to know how to do that, but this is the resonance hybrid. Anyway, so again, just to summarize from this number one, or for this first example that we're doing, because we'll go through the next ones a little quicker. The main reason that this happens, right, is we can delocalize this negative charge across both oxygens, therefore making this molecule more stable, okay? And in reality, the molecule exists as a combination of both of these structures, so both of these oxygen-carbon bonds are actually about 1.5 bonds in terms of length and strength. So the next option is the chlorate anion. Recall from chapter 2 that the chlorate anion is ClO3-, right? And we can draw a skeletal structure for that, and I trust that you'll do that if you need to, but I'm going to jump right in on this. Recall that chlorine is from group 17 on the periodic table, meaning that it has 7 valence electrons to be a formal charge of 0. Oxygen, being more electronegative than chlorine, will obviously be the atom that bears the negative charge, which gives rise to the overall negative charge on this polyatomic anion. So our central atom will be chlorine, right? There will be 3 oxygens bonded to it. And how do we get an oxygen with a negative charge, right? You'll recall from the Lewis structures video, we have a single bonded oxygen with 3 lone pairs. That means these other 2 oxygens need to have a neutral formal charge, so they need to be double bonded with 2 lone pairs, and then we'll throw 1 lone pair on the chlorine to give it a neutral charge. So, I bet you're wondering, well, what happens here, right? We're going to do the same thing that we did in the last example, and we're going to delocalize this negative charge across each of these oxygens, meaning that there's this kind of cloud of dispersion that happens to where the oxygens share partial negative charges. And we'll draw a resonance hybrid for this as well, so you can kind of see where this is coming from. But remember that the main thing that gives rise to this is that there's really no selectivity as to which oxygen bears that single bond and negative charge. And again, I'm just putting my formal charges in on the oxygen so I can keep track of what I'm doing. This works for me. If you don't need to do that, good for you. I prefer it. But again, as you do Lewis structures and resonance structures more, you'll get the hang of how to see these trends and identify the patterns that these molecules will follow. Right? So, this is the full expansion of the resonance structures for the chlorate anion. We, of course, can draw a resonance hybrid, where that Cl will, of course, be in the middle. In every structure, oxygen has at least 1 bond, right? And in some structures, it has 2, right? So we'll draw 1 bond to each oxygen, right? In every structure, chlorine has a lone pair. In every structure, oxygen has at least 2 lone pairs. And then we can put in our partial bonds and our partial charges to give rise to a little bit better of an explanation as to how this exists in normal chemical settings or nature or natural settings, right? So those dotted lines showing partial times that it's double bonds, but always at least 1 bond to each oxygen, and the negative charge is delocalized across all the oxygens, ultimately stabilizing this molecule. Just a quick reminder, though, that a big way that you can identify where there's resonance is that you can say, well, wait, is there any reason why a specific oxygen would bear that double bond or single bond, for matter of fact, or is it just an arbitrary thing of, well, 2 of them have to be double bonded, 1 has to be single bonded, so really it can happen at any of the 3 oxygen positions. So that is how you would go about chlorate. Now we're going to do a different ion. This is the carbonate anion. Recall from chapter 2 that the carbonate anion is CO3 2 minus, right? So you're going to have two formal charges of -1, or maybe one formal charge of -2. Ooh, you don't know, right? So pause the video and see if you can do this one by yourself. So while you were gone, hopefully this is what you wrote down. So these three resonance structures possible for the carbonate anion. Obviously this is a little bit different because now there's a double bond moving around to each position rather than a single bond, with the rest being double bonds like the chlorate anion that we just did. A couple notable things with this. So you'll notice that I didn't really do a work through with this one. It's really the same procedure as the chlorate one, so in the interest of keeping this video a little bit shorter, I was hoping you guys would write down your answers first. If not, rewind the video and try to produce these answers with your own deductive reasoning, rather than just writing them down from memory, although you probably could. Again, there's really no selectivity as to which oxygen is better than another oxygen to have that double bond. So again, it delocalizes that negative charge around all of the structure. Sorry, forgot my 2 minus. Remember, those brackets in the chart are really important, and resonance arrows are double-headed arrows that point between the two structures. Again, if we wanted to draw a resonance hybrid, that would be the case. So some people would argue that there's a partial positive charge on carbon. For the intents and purposes of general chemistry, I'm showing you guys that it's delocalizing around these. The negative charge is delocalizing around these oxygens. Worry about carbo-cation stuff and positive charges on central atoms in organic chemistry. This hybrid, again, is not something you need to know. It's just something as an explanation to you to show that in real life, this carbonate anion exists as a hybrid of all of these three resonance structures. So it exists in all of them all of them combined together make the total structure of how this exists in real life. And last one we're going to do is actually a molecular compound, is sulfur dioxide. So recall that sulfur dioxide is just SO2. Really quickly, you guys, be mindful that oxygen is very electronegative and likes to have electrons. Okay? So do the same thing that you did last time and pause the video. I'm going to pause my end of it, draw in the resonance structures, and then we will talk about why this is the case. So good luck. So if this is what you wrote down, good job. Sulfur dioxide is one of those interesting ones. It's different than what you'd normally think. And if you wrote down, so just a moment of gratification for you, if you wrote down this and said, well, it's the most stable, the formal charges are 0, I've satisfied all the electrons that need to be taken up, my valence electrons are done, everything's cool, then that's fine. So it turns out that sulfur can expand its octet, but this does violate the octet rule. And as this is a reasonable Lewis structure based on what you've learned, experimental data points to the hybrid model existing more than this one. So I love that you're using deductive reasoning, writing that down. Unfortunately, that's not correct for sulfur dioxide specifically, but good work. So why is it a group of hybrid structures rather than one Lewis structure? And this actually points a lot to electronegativity, and it turns out that as a total, right, oxygen likes to bear negative charges more than sulfur does, and oxygen is an electron hog. So half the time the oxygen on the right will hog those electrons from that oxygen-sulfur bond that you might have drawn in, okay, so reducing that double bond to a single bond, and half the time the other one does it. So we have this hybrid resonance structure at the bottom that shows us that each oxygen has a partial negative charge. These two dots right here are a lone pair on sulfur. They're not part of this, pseudo bond guy, right? But it actually turns out that this is a little bit more stable because A, that negative charge can be distributed, positives and negatives attract, right? And then also that this doesn't breach the octet rule for sulfur. And for this particular situation, sulfur would not want to break the octet rule, so this would be the favored structure. And it turns out that, or this, I guess, but again, it turns out that experimental data points to the hybrid model being the accurate structure for sulfur dioxide rather than 2 double bonds to oxygen from another group 16 atom or another chalcogen. So that being said, that's been the resonance video that we've done. I'm glad that I kept it to 15 to 16 minutes. That was the goal. Again, just a little recap. Remember, resonance happens when we can delocalize charges and make a molecule more stable that way. And a big way that you can identify when resonance is resonance is present somewhere is you can really tell, well, there's not a specific reason why one of these heteroatoms has to have a bond, or a specific type of bond rather, other than another atom of the same type. So again, we've done examples with oxygen because it's very electronegative, it's very easy to predict, and for all intents and purposes, it's what you'll run into in General Chemistry 1. This last example was kind of something that was more for your personal information and a little bit of exploration in the topic, but it's not something that I would personally ask you on a test. If you're watching this video from another institution and your teacher does want to use it on a test, obviously consult them. The explanation is pretty consistent for sulfur dioxide across the board, but other molecules that exhibit that type of behavior may have other reasoning for it. So again, always check with your instructor, check with your professor, do your research before you ask stuff or go wailing into an office. So anyway, that was a total tangent. Basically concluding and saying, remember, it turns out when there's no preference or selectivity, we get resonance. This results in an increase in stability, and the molecules actually exist as a combination of the structures together rather than one or the other in equal abundance. So I hope that cleared it up. We'll see you in Chapter 9.